record on this computer. There we go. Okay.
I need to press something.
No, I've set it up, so that's all good. So go for it.
Okay. Actually, you cannot see my pointer, right?
No, I can't see anything. Yeah.
Oh, that's weird. Okay, I'll just, and I can't just get out of here actually.
Yeah, it doesn't look like you're in presentation mode. It looks like we're seeing your screen, not the presenter thing.
Yeah, I mean, the computer just got stuck. So, oh, actually, yeah, I had, okay, so I can move back and forth. I'll just, yeah.
Okay, that's fine.
Oh, no, it's fine. Okay. Okay, so today I'm going to tell you about some work that we have been doing with mostly with people from Stony Brook, with Peisidou, who is a postdoc at Stony Brook, Ruben Essig, you all know Ruben, and Mukul, who is a grad student that is moving now to UC San Diego for a postdoc. And today I want to tell you about a series of experiments to detect dark matter that are seeing excess events at low energies. Okay. Now there's a wide variety of dark matter experiments looking for dark matter under the assumption that it has significant enough interactions with the standard model so that you can detect it. And since we do not know what's the mass of the dark matter particle, experiments aim to cover collectively the widest possible range of masses, ranging from a tiny fraction of an electron volt up to the Planck scale and even beyond. And within this very large range of masses, perhaps the most familiar experiments to you are the ones looking for the so-called weakly interacting massive particles, which are dark matter candidates with masses in the order of 100 of GeV, roughly. But today, I want to talk about experiments that look instead for dark matter in the SUB-GEV mass range, so in the mass window right below the WIMP. And there are several reasons, both theoretical and experimental, why people have been thinking lately about SUB-GEV dark matter. From the theory side, on the last 5 to 10 years, there has been lots of progress to understand and constrain models of SUB-GEV dark matter. So without trying to be comprehensive, let me just show you 2 examples of typical models that people have in mind for this mass range. Okay. So on one side, you have models in which you have a dark matter particle, which interacts with the standard model via a line mediator, which is usually a vector boson, usually a dark photon. Okay. Dark photons interact with the standard model electric charge. And these models have the nice features that, first of all, they have a consistent thermal history. You can populate the dark sector via this dark photon from the standard model thermal bath. And on the other side, these models are also detectable. So that's also a nice feature because you can build an experiment to detect dark matter scattering mediated by this dark photon, which then couples to electric charge. In such a scattering experiment, dark matter may deposit energy in your detector by, for instance, exciting an electron in a target from some ground state to some excited state. And then if you have a detector that is able to capture that energy deposition, read it out somehow, then you can gain access into the dark sector. A second type of models that people consider are models in which the dark photon itself is the dark matter candidate. In this case, these models are detectable because your dark photon can, for instance, get absorbed in some target by exciting an electron from a ground state into an excited state. And therefore, if you read this energy deposition, you gain access into the dark sector. Now, one of the first things that you need to understand about SUB-GEV dark matter is what are the typical energy depositions that you get from scattering or from absorption. So let's start with the case of scattering. So if you have a SUB-GEV dark matter particle that scatters out of a detector, then the maximal amount of energy that you can get out of this process is the kinetic energy of the dark matter. And assuming for simplicity that dark matter has a mass of an MeV, and knowing that the velocity of dark matter is a few hundred kilometers per second, then you get that the typical energy depositions that you get from this process are of the order of an electron volt at most. So this immediately tells you that if you want to detect dark matter, SUB-GEV dark matter scattering, you need experiments which have electron volt energy thresholds and hopefully electron volt energy resolution. So committing to these particular energy resolutions of order of electron volt, and now taking the case of dark matter absorption, which is our second model example, then of course, dark matter, these detectors can detect this dark photon absorption down to masses for the dark photon of roughly 1 electron volt, because then you get the whole rest mass energy of the dark photon. So for the rest of this talk, just for concreteness, I'm going to concentrate in these mass ranges, starting from an electron volt up to roughly a GeV. Okay, so that's what people call a SUB-GEV dark matter in this context. Now, the other motivation for this recent interest in SUB-GEV dark matter is that from the experimental side, precisely the developments required in order to achieve electron volt energy resolutions have been achieved during the previous years, like during the last 5 years especially. To give you an example of what experiments are capable of doing now, consider the case of experiments reading energy depositions in a CCD, a charge-coupled device. Okay. So I will tell you what's a charge-coupled device more precisely later, but for the moment, let's just think about it just like as some target that can read out energy depositions. Now, traditional CCDs, well, the way that a CCD works is that you absorb some energy deposition, which creates an electron-hole pair in a semiconducting target. Traditional CCDs had an energy resolution, which is shown here in this left panel. Okay. Traditional CCDs were able to detect energy depositions that lead to at least roughly 10 electron-hole pairs. Since to create an electron-hole pair in a semiconducting target, you require roughly an electron volt of energy, that means that the traditional energy thresholds of traditional CCDs were of the order of 10 electron volts. However, there has been lots of progress in this business lately. So on the right panel, I'm showing you the energy resolution of a new type of CCDs, which has been developed mostly in the last 5 years, which go under the name of skipper CCDs. And you see that the energy resolution has dramatically increased with respect to traditional CCDs. So now you see that these CCDs are able to detect single electron-hole events, which are associated with electron volt energy depositions. Therefore, you see from these figures here that currently dark matter experiments are able to detect precisely these electron volt energy depositions that we require to see SUB-GEV dark matter. Now, the combination of these theoretical and experimental developments has led to an explosion of experiments looking for light dark matter in the SUB-GEV mass range. So just to illustrate how active is this field, in these two panels, I'm showing you recent exclusion lines on these two types of dark matter models that I just showed you. Dark matter interacting with the standard model via dark photon, and dark photon dark matter itself. Okay. And you see that there are lots of lines. All these lines are exclusion lines that have been drawn here like in the last year to 2 years. So all these results are quite recent. And there's a variety of experiments that are looking for dark matter in this mass range. SENSEI, SuperCDMS, Edelweiss, and others. Okay. Currently, the best limits on scattering of dark matter out of electrons with a dark photon mediator come mostly from the SENSEI experiment in the SUB-GEV mass range, but there are other experiments that are competing. And moreover, towards the future, there are many other proposals that try to aim for this range of masses. Okay. Now, interestingly, the majority of these experiments, if not all of these experiments, have seen excess events at low energies, okay? And they do not understand what's the origin of these excess events. So the bold theorists will say that perhaps these experiments have detected dark matter, and those excess events are precisely the scattering or absorption of dark matter in the target detector. However, more conservatively, it's not surprising that these experiments are seeing an excess of events at low energies, because we're testing the standard model in a kinematical regime, which we didn't test before up to now. And therefore, it's very likely that you are bumping into backgrounds which you didn't understand before. To illustrate these excess events at concrete experiments, for the rest of this talk, I'm going to concentrate on two particular dark matter experiments. One is SENSEI and the other one is SuperCDMS. Both of these experiments try to detect dark matter by scattering or absorbing dark matter in a semiconductor target, which leads to the creation of an electron-hole pair, and then they read out these electron-hole pairs. So these two plots here, they are a representation of the excess events seen by both SENSEI and SuperCDMS. So let's start with SENSEI. So SENSEI categorizes their events in the number of electron-hole pairs that are created by event. And these points here are the number of single electron-hole pair events that they saw during their latest data taking process, okay? And this is plotted against some cut in their analysis, which is called the halo radius. I'm going to explain to you what's that later. But for now, it's just a parameter of their analysis. And the thing that you have to see from this plot is that the rate of one electron events that they are seeing is non-zero, although they were expecting to see 0 if it will have been a search with 0 backgrounds, okay? So they do not have an explanation for the origin of these single electron events at SENSEI. On the other hand, SuperCDMS HVeV tries to detect electron-hole pairs in a completely different way than SENSEI. They have very different technology, and I'm going to explain to you what's the difference between these experiments later. And they also categorize their searches in the number of electron-hole events which are created by event. So here, for instance, they have the single electron-hole beam, 2 electron-hole beam, 3 electron-hole beam, etc. And these lines here are their data, and they are showing that they are seeing peaks in all the n electron-hole beams. And they do not understand the origin of these peaks, with the exception of the peak in the 1 electron-hole beam. The 2 to 6, they do not understand, okay? So I'm going to try to convince you for the rest of this talk that the origin of these events, both at SENSEI and SuperCDMS, are not dark matter, but instead that they are processes, normal standard model processes, which were not accounted for before.
Daniel, can I just make sure I understand both these plots correctly? Because I've seen these kind of things before, but I'm not sure I get it. So on the left plot, the SENSEI plot, the only thing I'm supposed to notice is that the data points, no matter what value of the halo radius I pick, is not 0, right? It's like exactly. 400. Okay. And on the right-hand plot, it's really the blue line I'm supposed to look at. That's the one that has some calibration. It's the
dark matter search line. This is their calibration. This is they calibrated their detector with a laser, the blue. That's the laser calibration. So the dark matter search is the solid line.
I see. So I'm supposed to look at the red line, and I see that the red line has peaks at each of these things.
Exactly.
And the black line is what, a theory prediction of what some random
exactly
dark matter. Okay, so I see.
Exactly.
Thank you.
Okay, so so I'm going to try to convince them that these events are standard model. Okay, and the origin of these events are going to be 2 processes, which are pretty well known. One is Cherenkov radiation, and the other one is recombination of electron-hole pairs that were created by tracks. So both of these processes arise when tracks pass through your detector target or any auxiliary materials around your detector. And I will show you that these 2 processes can explain the excess events both at SENSEI and SuperCDMS. Now, these processes are standard, but somehow their importance in light dark matter detection had not been realized before. Okay? Now, before going and explaining to you what are these 2 processes in detail, and reminding you what are these 2 processes in detail, let's first take the big picture idea on how these background events are being generated at SENSEI and SuperCDMS. So the idea is that SENSEI and SuperCDMS detect electron-hole pairs. So they detect the excitation of an electron from the valence band of a semiconductor to the conduction band. Okay? There are different ways in which that process can happen. But in particular, one possibility is that if you have background photons which have energies of order an electron volt, they can excite an electron from the valence band of their semiconductor target, which is silicon, to the conduction band. Now, if this is going to be your background explanation, that you have low energy photons flying around in your detector, you need to explain to me what is the origin of these low energy photons. And it turns out that the origin of these low energy photons are tracks, that means electrons or muons, electrons from radioactivity from the wall of your detector, from the materials itself, etc., and muons from the atmosphere that pass through your detector itself, radiating Cherenkov photons or creating electron-hole pairs, which then lead to radiative recombination events, or that pass to any auxiliary materials that are holding your detector. So a typical detector schematic has a detector target, and usually you have holders around it, some plastic things that just make sure that your detector stays in the same place. And usually you also have some metallic housing around the detector. So any photons that you create from radiation, either from the detector target or from the holders, which are plastic, they will bounce around in your metallic enclosure until they are eventually absorbed somewhere. Since by definition, your detector is an absorber, the most likely place where these low energy photons will end up will be in your detector itself. And therefore, they will be able to be registered as an event and they will be able to mimic dark matter. Moreover, I will show you that Cherenkov photons generated by charged tracks and radiative recombination events are quite abundant in experiments. Therefore, they can rather easily explain the excess events that we are seeing in SENSEI and SuperCDMS. Okay. So let me now remind you what's Cherenkov radiation and what's radiative recombination. So Cherenkov is very simple, so it will take us just 2 minutes. Radiative recombination is a much more complicated process. We'll have to go in that in a bit more detail. Okay. So let's start with Cherenkov radiation. So the Cherenkov process is the spontaneous emission of light by a charged particle that passes through a dielectric material. Okay. So the diagram for this process is shown here. Now, this process, of course, does not happen in vacuum, and that's reflected in a condition for Cherenkov radiation to arise, which is this condition that I'm writing here. This condition tells you that the velocity of your charged particle squared, be it an electron or a muon, times the dielectric function of your material needs to be larger than 1 for Cherenkov radiation to occur. So just as a reminder, the dielectric function of a material, it's a quantity that tells you how a photon propagates in that material, and therefore it depends on the energy of the photon that you're talking. Now, from this condition, since the velocity of a particle is always less than 1, you immediately see that Cherenkov radiation can only arise in materials where the dielectric function is larger than 1. Therefore, this process cannot happen in vacuum, because in vacuum, the dielectric function is exactly equal to 1. So this process only happens in dielectric materials where this function can be larger than 1. Now, given that said, Cherenkov radiation has a couple of very well-known characteristics. One of them is that the photons are emitted from the track in a very specific angle, which is called the Cherenkov angle, which you can calculate from the velocity of your particle and the dielectric function of the material. And secondly, the rate of Cherenkov photons per unit frequency of the photons emitted per distance traveled by the charged track is simply proportional to 1 power of the fine structure constant. So the Cherenkov rate is a very simple expression. Now, why is Cherenkov radiation important as a background for light dark matter detectors? There are 2 important reasons. First of all, Cherenkov radiation leads naturally to photons that have energies close to the electron-volt scale. Okay, so that we can see directly from the dielectric function of materials. Okay, so remember that the Cherenkov condition tells you that this inequality must be satisfied. And for this inequality to be satisfied, since the velocity of any particle is always less than 1, the dielectric function needs to be larger than 1. So let's take a look at typical dielectric functions of semiconductor targets, for instance, germanium or silicon. We see that the dielectric functions are large for energies below roughly 4 electron volts. And for energies above 4 electron volts, the dielectric functions plummet and become smaller than 1. Therefore, Cherenkov radiation in silicon or germanium can only happen for energies roughly below 4 electron volts. So that means that the photons that you get from the Cherenkov process naturally lie within your event range, the typical kinematics of your events, a few electron volts. Okay? So that's one reason why Cherenkov is important for light dark matter detectors. Another reason is that the Cherenkov rate is large. So the Cherenkov process happens at leading order in electrodynamics is proportional to only 1 power of the fine structure constant. And therefore, the number of Cherenkov photons that you get per track is pretty large. For instance, consider an electron track, which has roughly 100 keV, which travels then usually 100 micrometers in silicon before being stopped. And then let's calculate how many photons within an energy range of like 1 electron volt are emitted by this track. And the result is that you get roughly 4 Cherenkov photons per track. And usually in light dark matter detectors, you have several tracks passing through your material. Therefore, it's very easily you can get hundreds of Cherenkov photons within your detector exposure. Now, this needs to be compared with other radiative processes, such as, for instance, Bremsstrahlung, which is a process that happens when an electron scatters out of a nucleus and emits a photon. This process happens at third order in electrodynamics and therefore is suppressed with respect to Cherenkov. And you can actually check that in typical silicon experiments, the rate for Bremsstrahlung emission of low energy photons, it's roughly a couple of orders of magnitude smaller than the rate for Cherenkov emission. Okay. So let's now move on to radiative recombination, which is a much more complicated background. Okay. So radiative recombination, happens when electrons and holes that were excited in a semiconductor return to the ground state. They recombine. And there are several ways by which they can recombine, but one way is that they can recombine by emitting a near bandgap photon. Okay. Now, why is radiative recombination important? Again, first of all, it's important because the photons that you get out of this process are naturally close to the electron-volt scale, which is your definition of an event in a light-dark matter detector. So, and that happens because the typical band gaps in semiconductors, the energy across this electron-hole pair recombination, it's of the order of an electron volt. In silicon, it's 1.14 electron volt, etc. Okay. So that's one important reason why radiative recombination is an important background. And the second reason why radiative recombination is an important background is that tracks, electrons or muons, actually leave most of their energy in a material, not in the form of Cherenkov radiation nor Bremsstrahlung. They leave most of the energy in a material in the form of the creation of electron and hole pairs. Okay. For instance, a single 200 keV electron track traveling in silicon travels 200 micrometers before being stopped. That's the mean range of an electron track in silicon of this energy. And you can calculate how many electron and holes are created as the tracks passes through silicon. And the answer is that you get 60,000 electron hole pairs. Okay. So this is clearly a large number of electron hole pairs. And if they all recombine radiatively, that will lead to a gigantic background of 60,000 near bandgap or electron volt energy photons, which then will be a huge background in any experiment. However, it turns out that not all electron hole pairs recombine radiatively. And in fact, only a minor fraction of them recombine radiatively. In calculating the rate of electron and hole pairs that recombine radiatively, it's a very complicated task. The reason is that there are competing processes. So the situation is the following. A track passes through your detector, creates a lot of electron hole pairs, creates a cloud of electron hole pairs roughly shaped as a cylinder around the track. And then these electron hole pairs start diffusing. So there's a diffusion equation that controls how the dynamics of these electron hole pairs after the track passes by. And not only these electron hole pairs diffuse, but also there are competing processes by which they recombine. One is radiative recombination by the emission of photons, and other processes are non-radiative recombination processes by the emission of phonons instead. Okay. And you need to calculate how these processes compete in order to finally calculate how many of these electron hole pairs recombine radiatively leading to photons. Okay.
So Daniel, just to ask, so is the reason why we're mostly worried about these radiative recombinations that, so okay, these tracks will generate a lot of electron hole pairs, which is what, say, SENSEI is looking for, but it generates so many that we can just reject it really easily. The danger is that we generate a photon that then goes somewhere else, and then we don't reject that. Is that the logic?
Exactly.
Okay, cool.
Exactly. And I'm going to show you like very concrete examples of precisely that process later with pictures and everything.
Cool, thanks.
So, so let's try to estimate how many photons do you get from this. Okay. So let's compare the different competing processes. So the first competing process is diffusion. So you have all these electron hole pair clouds. In order for them to recombine, an electron needs to find a hole. However, after the track passes by, the electrons and the holes start diffusing, so they start getting away from each other. So it becomes harder for them to recombine. So recombination clearly competes with diffusion, at least in undoped semiconductors where the only electron hole population is the one left by the track. The situation is very different in doped semiconductors. The reason being that in a doped semiconductor, in addition to the electron and holes that were left by the track, there's a background population of electrons or holes which are donated by the dopant. So even if the electrons and holes that are left by the track, they diffuse away from each other, they can always then find somewhere else in the bulk of your doped semiconductor a hole to recombine, which is given by the dopant. So diffusion is not a competing process for radiative recombination in doped semiconductors. And in undoped, it's detrimental for radiative recombination. But even if diffusion were not a competing process to radiative recombination, there are still other processes which compete. For instance, non-radiative recombination via the emission of phonons. In particular, there's a process which is called trap-assisted recombination. The idea here is that if you create an electron and a hole pair and you find an impurity in your bond structure by some metal, some tiny trace of some metal that was left out, for instance, in your semiconductor, those impurities lead to some energy levels in between the conduction band and the valence band. And what can happen there is that an electron goes first into this intermediate state, which is called a deep trap, and then recombines with the hole. And that process happens via the emission of phonons. And it turns out that this is one of the leading processes by which electrons and holes recombine in materials. However, the calculation of this process requires knowing how many impurities do you have in your material, which usually is a number that you do not know. So you need
Sorry, is there a quick understanding for why it's better to have that intermediate level than to just fall all the way?
Yeah, the reason is that the energy splitting here is 1 electron volt. So if you want to go from here to here, that means that either you emit lots of very hard a few very hard phonons, or lots of very soft phonons. So it's a very high order calculation in perturbation theory. If you have the intermediate state, you can emit softer phonons and it becomes easier for you to go down.
Okay, thanks.
So why does diffusion not suppress this process? Because both the electron and the hole have to find the same impurity. Right?
Absolutely. So diffusion also competes with non-radiative recombination. So diffusion competes with both radiative and non-radiative recombination. But we're only interested in the processes that compete with radiative because we want to calculate the radiative rate. So given this set, now we're able to estimate how many photons recombine radiatively. Okay. So let's take the case of undoped silicon, where diffusion is the main competing process to radiative recombination. So how do you calculate how many photons are created by our example track, which was an electron of 200 keVs that traveled 200 micrometers in silicon, leaving 60,000 electron hole pairs? How do we calculate that photon rate? Well, we know that the number of electron hole pairs is 60,000 from our example. And now we need to calculate the branching fraction to go radiatively, for them to recombine radiatively. And that you do by comparing the diffusion timescale with the radiative recombination timescale. And I have calculated those timescales for you in typical high purity silicon. And it turns out that the number of photons that you get, even though you get 60,000 electron hole pairs, it's 10 to the minus 5, between 10 to the minus 5 and 10 to the minus 4. So it's a tiny number, okay? So that means that diffusion strongly suppresses radiative recombination in undoped silicon. The situation is completely different in doped silicon. So let's take the case of doped silicon now, and let's dope it with a concentration of, say, p dopants or n dopants of 10 to the 18 per centimeter cube, okay? Which is a high concentration, but it's not particularly high. Then the main competing process for radiative recombination is not diffusion, it's instead trap-assisted recombination. And taking typical values for the trap-assisted recombination time in silicon, you get that the number of photons that you get from this track that left 60,000 electron holes is roughly 600, which is a huge number. So if we compare it with the number of Cherenkov photons that we were getting per track, this number is 2 orders of magnitude larger. So this immediately tells you that radiative recombination, even though it's not an important source of backgrounds in undoped semiconductors, it's clearly an important source of backgrounds in doped semiconductor targets. Okay, so we will see how this arises in particular in SENSEI. And let me just point out that this is a new background that had not been pointed out before, differently from Cherenkov radiation, which had been already thought of in the context of WIMP searches at low masses. Okay. Okay, so now we're ready to understand how these backgrounds arise both at SENSEI and SuperCDMS. So let's start with SENSEI. So SENSEI took data in 2020 and they had an effective exposure of roughly a gram day, okay? The SENSEI experiment uses a SCHEMATICS, a charge-coupled device, to detect electron-hole pairs that can be created by the scattering of dark matter. SENSEI was located 100 meters underground in a cavern, the Minos cavern at Fermilab, and the CCD, which is shown here, was surrounded by some copper tray, which is shown here, and had some additional shielding around it. Okay. So before moving on, let me remind you how does a CCD work so that we understand how these backgrounds arise. So a CCD, a charge-coupled device, it's an array of coupled pixels, semiconductor pixels, shown here. Okay. The idea of detection is that in any of these pixels, a dark matter or a photon or something can come in and excite an electron-hole pair. After the electron-hole pair is created, it's drifted around in the CCD down to the readout stage. Now, CCDs, and in particular the SCHEMATICS CCD used by SENSEI, does not have good timing resolution. This whole process is very slow. So the readout process of electron and hole pairs in the SCHEMATICS CCD of SENSEI takes 5 hours. Therefore, the way that SENSEI works is that it exposes their CCD to scatterings of dark matter or whatever background you have for 20 hours, then it stops the exposure, and then it reads out the electron-hole pairs in a second process which takes 5 hours. Okay, so that's the way that SENSEI works. Now that means that SENSEI does not have
this is not necessarily relevant, but can you explain intuitively why it takes so long to do this? Like the thing is really, I mean, the actual detector is very small.
Yeah.
What takes so long?
It's because you have many pixels and you have to read them one at a time, and also the SCHEMATICS CCDs of SENSEI, one of the ways that they reduce backgrounds is that at the readout stage, they do not measure the electron and hole pairs once, they read them out like several thousand times. They put them in readout, they put them back, readout back, readout back, because in that way they reduce the noise in the readout stage by 1/√n, where n is the number of readouts that you have. So in total, doing the whole process takes a long time.
Hmm.
So
just one more question about this. I mean, your things have to hang around for 5 hours or so, so your electron hole pairs have to be extremely long-lived. Is that
no, but there's a way by which they put an electric field, so they keep them separated and they only read the holes. So this has an electric field across.
Okay.
So once the electron hole is created, it stays there.
Okay, so does that affect the calculations that you were doing for the other thing as well? Because you were looking at how electron hole pairs recombine and stuff. Does that affect any of those?
No, you will see what's going to happen for the electron hole pair recombination. So for
okay.
it will happen in a different part of the CCD, which is not subject to an electric field.
Okay, got it.
Okay. Okay, so SENSEI does not have timing resolution, and that means that in particular it cannot veto high energy events such as tracks, electrons, or muons using timing. And instead it has to use a geometric position to veto tracks. So for instance, this is a typical image of the CCD of SENSEI. So the long energy depositions here are muons, the shorter ones, these curly ones, are electrons, the bright dots are X-rays, and the very tiny dots here, they are actual events. Okay. Now, how do you get rid of tracks? Because tracks are clearly not dark matter, so you need to mask them out. So what SENSEI does is that it draws a radius around the track, and it drops all the pixels of the track and of all the area within that radius. Okay, so that's called the halo radius cut. And in their analysis in particular, they take the track, they mask 60 pixels away from the track in all directions, and they remove all those pixels from their analysis. Okay. So that's the way that SENSEI rejects tracks. With their standard analysis, they used a 60 pixel halo radius, and they found still that the rate of single electron events, even after masking out these pixels, is 450 events per gram day. And they know two things about this background. First, they know that they depend on the number of tracks that pass through your CCD. So here they measure the rate of single electron events with lots of tracks passing through the CCD and with few tracks passing through the CCD by modifying the shielding around the detector. And they saw that with more tracks, you get more single electron hole pairs. With less tracks, you get less single electron hole events. Okay, so this background is clearly related with the number of tracks. On the other hand, they also know that the background decreases as you increase the halo radius or the halo mask. In other words, the more area you mask around the track, the less backgrounds you see. The closer you go to the track, the more backgrounds you see. So that clearly tells you again that these backgrounds are related with the tracks. But now you have to find the origin of these backgrounds if they come from tracks. And in order to understand that, let's take a look at a schematic view of SENSEI. Okay. So SENSEI looks as follows. This is the cover tray that I showed you before. And within this cover tray, you have the skipper CCD, which is their detector. There's a pitch adapter, which is nothing else than a piece of silicon that holds the CCD, and some glue in between, which is epoxy. Okay. And let's see how backgrounds are going to arise in SENSEI. So let's start with Cherenkov, which is easier. So Cherenkov backgrounds are going to arise because tracks are going to pass through your pitch adapter and your CCD, and they are going to lead to long-lived photons that long-lived Cherenkov photons that get away from tracks. Now, these photons afterwards, they will bounce around in the surfaces of your CCD, or they will bounce around in the copper, etc., until they are eventually absorbed somewhere. And the two main chunks of material where they can get absorbed is in the CCD itself or the pitch adapter. They have roughly the same dimensions, so it's roughly half and half. Half of the photons gets absorbed here, half here. Moreover, the photons cannot escape because you have a copper vessel. So any photon that makes it to the copper will just bounce back because copper is just like a mirror for these low energy photons. Now, then from what you should get from this is that in order to calculate the backgrounds, you need to keep track of these photons as they bounce around in the surfaces. And this simulation is extremely complex. Just to give you a hint on how complex is the simulation, let me show you a magnification of the upper surface of the CCD here. So this CCD here has silicon, and then it has some flat surface here. But then after that, you have a bunch of materials with very irregular surfaces, such as thermal oxide, polysilicon, silicon dioxide, etc. Okay. So if you want to calculate how these photons are going to bounce back in the surface, you need to solve for the propagation of the photon along these very thin films. You have thin film interference that makes the process complicated. So keeping track of how these photons bounce around is a highly non-trivial thing to do. Okay, so for that you need to build a simulation, which we have done, and we'll show you the results later. But let's now move on to radiative recombination events.
Daniel, why does it matter that much? Like, if you know that every photon eventually gets absorbed, then why is it not basically just, you know, roughly volume of, or effective volume of the CCD versus effective volume of everything else in the
Right, because you may worry that they may get absorbed more in the pitch than in the CCD, for instance. Photons may escape the CCD and then get trapped in the pitch somehow due to the irregularities in the surfaces and get absorbed there. Another reason why you may worry is that once you generate a photon, it will travel a particular distance before getting absorbed. Okay, so let's say that it just gets out of the CCD and it makes it through the pitch adapter. Then it's likely that it will get absorbed here because to get back to the CCD, it needs to bounce back to the CCD, travel a lot, and that's unlikely. So in order to see the photons escape the CCD, you need to see how do they reflect out of the surfaces.
I see. And why, so your earlier estimates of Cherenkov radiation were like 4 photons are left by any given track.
Yeah.
But then you said that each track also gives me like 600-ish radiative recombination photons as long as the silicon is doped. So why do I even care about Cherenkov? Are the radiative recombination events not the overwhelming majority of what I would expect? Or is this semiconductor not doped enough for these?
Exactly. So the idea is that most of the semiconductors that you find in here are not doped.
I see.
So let's move on to radiative recombination and you'll see what happens. Okay. So radiative recombination is much more complicated, and actually we didn't realize about this background until very late in this when we were studying this issue. Okay. So the idea is that tracks will pass through the CCD. However, the CCD is highly pure silicon, so there's no doping in the CCD. However, in the backside of any CCD, there's a very thin layer of doped material. So in particular, in the backside of the CCD of SENSEI, there's a layer of like roughly 5 micrometers of a phosphorus doped semiconductor. And the dopant concentration is very, very high. It's around 10 to the 20 per centimeter cube. This layer is thin, it's roughly 5 micrometers, but as Jed was pointing out before, the number of radiative recombination events that you get from a track is gigantic. So even though the layer may be very thin and tracks will pass through that layer only from a very specific, just for a very specific trajectory, then the number of photons that you can get out of that is huge. Therefore, you may worry that this is a source of concern. And in fact, it is a source of concern, and I will show you that. So the idea then is that you will generate near bandgap photons close to the back of the CCD, and they will travel and make it into the CCD and be absorbed there, mimicking in this way an event. Okay. Now, as Robert pointed out before, photons that are close to tracks, they will get vetoed. So in order for them to constitute backgrounds, they need to travel far away from tracks. So that's also why you don't care about electron-hole pairs close to tracks, because all the pixels close to tracks are vetoed. So you only care about photons that get far away from tracks and create an electron-hole pair far away from the track that then is read out as an event. However, photons can be long-lived in the semiconductor target, in the silicon. The reason being that if this is a plot of the mean free path of the photons versus its frequency. And you see that the mean free path becomes really, really large as the frequency approaches the silicon bandgap. And in particular, if the frequency is below like roughly 1.2 electron volts, the mean free path of a photon is larger than 60 pixels. Therefore, it avoids this halo mask cut of 60 pixels that SENSEI imposes. Now, all the radiative recombination photons, by definition, they are near bandgap because they arise for the recombination from an electron and a hole. Cherenkov photons, on the other hand, they have all energies from 0 electron volts roughly up to 4 electron volts. So not all of them are near bandgap, but some of them are. So all the photons with energies roughly between 1.1 and 1.2 electron volts, they will travel long distances, they will get far away from tracks, and they will be registered as events. So let's see how this happens in SENSEI. So this is our simulation. So this is a simulation of tracks passing through the CCD of SENSEI. So these long tracks are muons, the shorter tracks are electrons, the dots are X-rays. And this is the same simulation with the Cherenkov photons absorbed in a given pixel in orange, and the radiative recombination photons absorbed in a given pixel in black. Okay. So there are two things that you see from this picture. First of all, most Cherenkov photons, as is expected, they get absorbed close to the tracks because they are mostly energetic. But some Cherenkov photons get away from tracks, like these ones, this one, etc., because they turn out to be coincidentally near bandgap. Okay. On the other hand, radiative recombination photons, which only happen in the backside of the CCD, all of them, by definition, are near bandgap, so all of them are long-lived, so they are more evenly distributed along the CCD. They travel a lot, and they get absorbed randomly in some random part of the CCD. Okay. So with this simulation, the latest estimate that we get for the rate of single electron events with large systematics is 240 events per gram day. This has to be compared with the 450 that SENSEI observes, and then you may say that this rate is a bit low. This error is just statistic, but consider two things before concluding that this rate is a bit too small. First of all, there are large systematics on this rate, and the systematics likely take this rate upwards. One of the important systematics is for instance, for radiative recombination. In order to calculate how many radiative recombination photons you get, you need to know the number of impurities in your material, which you do not know. So there's no measurement of the number of impurities in the backside of the silicon CCD of SENSEI. So we have no data of that. So we have estimated the number of photons that you can get from just like from other similar pieces of silicon that people have measured, but we have no idea if the high purity CCD of SENSEI can have less impurities, in which case you can boost the rate of radiative recombination. And this rate is roughly half Cherenkov, half radiative recombination. Okay. So if you boost the rate by 100 events, say from radiative recombination, then you get closer to 450. So those are all things that we're now considering. There are other uncertainties in our calculation. One of them is the epoxy that is in between this CCD and the pitch adapter. We don't know the properties of the epoxy very well. In particular, we don't know how absorbing is it. If it's more transparent than one we think, this rate can also get a boost. But whatever this final rate is going to be, clearly the number of photons that we're getting, the number of events that we're getting, roughly 100 from radiative recombination, roughly 100 from Cherenkov, it's within the ballpark of what SENSEI is seeing. Moreover, there's more convincing information that the explanation that we have is the right one. So one of the things that SENSEI did is they measured the rate of single electron events as a function of this halo radius. And they saw that it decreased with halo radius. This is their data. And I already showed you a similar plot to this one. This is our simulation. So our simulation clearly reproduces, even though it's shifted down, clearly reproduces the right shape. And the reason why it does so is because the Cherenkov photons, most of them get absorbed at low radius, and only few of them get absorbed at larger radius. And this rate tends to flatten out at larger radius, but that's where radiative recombination comes in, because that radiative recombination photons do not care about the halo mass, because most of them are long-lived. So clearly the behavior of this rate, it's being matched by your simulations.
Sorry, just to ask one more question. Could you also look at the statistics of where you see these things as well? I mean, some areas of the thing are going to have more tracks than others just by random chance. And if the things travel some distance from tracks, that should lead to some spatial distribution of the one electron events as well. Is that something you've looked at?
Absolutely. One could do that, but we haven't done that with respect to the SENSEI data. So that's something that the SENSEI collaboration should do. But yeah, one could look at spatial correlations.
Okay, cool.
But yeah, there's no data released by the collaboration regarding that. Okay, so let's move on now to SuperCDMS. So SuperCDMS took data in 2019. It had a similar exposure to SENSEI, roughly a gram data. So the SuperCDMS experiment is very different from SENSEI. The idea of the SuperCDMS experiment is that a dark matter particle scatters out of a silicon target, creates an electron-hole pair, and then within that silicon target, you put the electron-hole pair in an electric field that drifts the electron and hole up and down respectively. And as that drifting is happening, many phonons are emitted via a process that's called the Egaña-Ugrinovic effect. Then SuperCDMS reads those phonons via a TES. Okay, so this is a picture of the SuperCDMS. You have the silicon target here, some electric field around it, and there are some PCBs that clamp this silicon, some plastic circuit boards, and the TES is here. The experiment was located on the surface at Northwestern, and therefore it was exposed to many tracks because it was on surface. Differently from SENSEI, SuperCDMS has excellent timing resolution. So their events are classified by whatever happens within a very short time window of 100 microseconds versus the 20 hours of SENSEI. Therefore, SuperCDMS uses that timing information to reject tracks that pass through your detector, for instance. And also it uses that timing information to define what's an N-electron event. So an N-electron event is whatever number of electron holes you created in your silicon target within roughly that 100 microsecond window. And they reported data regarding their N-electron event rate, with N ranging from 1 to 6 in their latest paper. And they see an anomalously large rate of events for all the beams, single electron event beam up to the 6 electron hole event beam. The single electron event beam, they think they understand. They think that it arises by the spurious creation of charges in the surfaces of their detector. But the 2 to 6, they have no idea what it is. Okay, so that's where our explanation is going to kick in. And in order to see how our explanation is going to work, let's look at the schematic of SuperCDMS. So SuperCDMS has their target detector, which is some silicon, and some plastic circuit board on the bottom, and some on the top, and some plastic connectors around. Okay. So first of all, to the best of our knowledge, there's no doped semiconductors in this setup here. So we're going to drop radiative recombination. And we're just going to concentrate on Cherenkov radiation, which happens even in the presence of purely undoped semiconductors. So let's first look at tracks that pass through your detector, the silicon piece, okay? Those will create Cherenkov photons that will be events. However, SuperCDMS has excellent timing resolution, so whatever passes through this detector gets immediately vetoed. So that's not a background. However, the PCBs, both the lower PCB, the upper PCB, and the plastic connectors, they are not instrumented. So any track that passes through the PCBs does not get vetoed and can generate lots of Cherenkov photons that then can bounce around in the metallic walls of your detector until eventually making it into the SuperCDMS detector. Calculating the number of Cherenkov photons that are created by tracks in the lower PCB or the upper PCB is not particularly complicated. And the result that you get is that the number is ginormous. It's gigantic. You get a gigantic number of Cherenkov photons. The problem is that now you need to calculate the probability for a photon to bounce around and make it eventually into your detector and be absorbed in your detector. And for that, you need a precise simulation and you need precise details of the detector, which we don't have. So we're not going to make that simulation. But then how can we estimate if this background is actually the thing that is explaining the 2 to 6 electron hole beams in SuperCDMS? And the way that we're going to do that is the following. We're going just to ask how many photons of all the Cherenkov photons that we created need to be absorbed in the detector for us to explain the rate correctly. And it turns out that if you feed that number to data, you find that if as few as 1 Cherenkov photon out of the 1,000 that you created makes it eventually into the detector, you can explain the observations of SuperCDMS. So that the smallness of the probability that you need for the Cherenkov photons to be eventually absorbed in the material, for you to explain correctly the rate, it's indicative of how large is the number of Cherenkov photons that are being created by these tracks passing through the CCD, so through the PCB. Now you may say that this is not a successful explanation of the backgrounds because we are feeding the overall number of Cherenkovs in the end to data. Even though the smallness of this number is highly suggestive that this is the origin of events, you are still feeding it to data, so you may say that this is not a very convincing explanation. However, that's not entirely fair because we're feeding the overall distribution of Cherenkov, of the absorbed Cherenkovs, but we're not feeding the shape of the distribution. In particular, SuperCDMS has data for the 2 to 6 electron beam, and that has a very specific shape. So under the assumption that the probability for you to absorb eventually the Cherenkov photon is 1 in 1,000, probability of 10 to the minus 3, we can calculate the spectrum that SuperCDMS should see if the events are Cherenkovs in the PCB. And this is the result that we get. So this is the rate. This is the observation of SuperCDMS, the solid lines, and the dots are our calculation. So you clearly see that the dots in the 2 to 6 electron beam very precisely match the data. The single electron beam, we cannot explain, but that's fine because SuperCDMS, anyways, they have an idea on what's the origin of these events. So this is quite convincing evidence for the fact that these events are just Cherenkov, together with the fact that only 1 out of 1,000 needs to eventually make it into the detector to explain this background.
Just to ask something. So this is presumably coming from the fact that the Cherenkov radiation has some power law with frequency.
It's not that.
Oh, it's not that.
This is just the fact that if you can calculate how many Cherenkovs are produced by track as they pass through the CCB, say PCB. Sometimes you emit 5, sometimes you emit 4.
That. So it's not the energy, it's just the number that you get.
It's that plus the fact that Cherenkov radiation has a specific, so the Cherenkov radiation has a roughly flat distribution. Mm-hmm. However, the PCB has a frequency-dependent absorption coefficient. So not all the Cherenkov photons get out of the PCB. So then you gain some frequency dependence from that. So you get some high energy photons that escape, some low energy photons that escape, and then you can ask what's the probability for them to get absorbed, and given their energy, how many electron hole pairs do they create, and then you get the distribution that we're seeing here.
So yeah, so the question was more like, if you just assume that if this is mostly coming from, say, Poisson, if you just put in a Poisson distribution, how good would the fit be relatively? If you just said, okay, let's assume that these things are Poisson.
It's a bit worse. It's still okay, but it's a bit worse.
So the frequency dependent stuff that goes along with the Cherenkov explanation does seem to make it better.
Yes. Well, it's not Cherenkov, it's just the absorption coefficient of the PCB that is frequency dependent.
The fact that you were generating it in this way, yeah.
Yes.
Okay, cool.
Daniel, did you say this and I just missed it? But the reason radiative recombination events aren't interesting here is just because there's not enough doped silicon sitting around?
To our knowledge, there's no doped silicon around.
Okay.
There may be, but we don't know. And if there is some doped silicon, I could think that there's some doped stuff, but it's probably in the detector. And if it's in the detector, anything that passes through the detector will get immediately vetoed.
Yeah. Okay.
So because they have timing. So I wouldn't be so worried about that in particular for SuperCDMS, although I cannot swear it by heart that it won't be a problem.
Okay. Thank you.
We just don't know enough about the detector. Okay, so these backgrounds are bad. If you have a lot of backgrounds, then clearly your dark matter can be hiding under these backgrounds. And so that's bad. So how do you mitigate that for the future? And how do you increase the reach to dark matter? So first of all, let me say that even though here I concentrated on SENSEI and SuperCDMS, these backgrounds are rather universal. So most detectors have similar setups. They have some detectors, some metallic housing around it where photons can bounce around. You have some dielectrics where Cherenkov radiation can happen, etc. So this is a concern for not only for SENSEI and SuperCDMS, but for experiments more generally. So what can we do towards the future? So first of all, one trivial thing that can be done is, of course, to increase shielding. So that's the experiments already do that, so that they remove tracks. They do not let tracks pass into your detector. But yeah, so that's one obvious way. So let's move into the second mitigation strategy, which is less trivial, which is the fact that if you want to reduce Cherenkov backgrounds in particular, you better minimize the amount of dielectric materials around your detector. So for instance, at SuperCDMS, the big problem was that they have two big chunks of plastic up and down from the detector. And those chunks of plastic are extremely efficient at emitting Cherenkov. But you need something to hold your detector. So how can you get rid of the plastic? Well, you can replace any holders, which are either plastic or Teflon, which are dielectric materials, with, for instance, metals, which do not emit Cherenkov radiation. If you do not want to use metals for some other experimental reason, you can still use plastic, but coat it in some metallic coating so that any Cherenkov radiation that is created in your plastic stays inside the plastic. It cannot make it out. Okay, so that's one possibility.
Just to ask, if you have metals, you also have transition radiation from those. That's just numerically less of a worry then?
Transition radiation is almost always, if not always, numerically less relevant. Okay. And the reason is that the rate is roughly alpha times the number of surfaces that you encounter. However, the rate for Cherenkov is alpha times the distance that the track traveled, which always turns out to be larger.
Yeah, sure. It's a volume effect rather than a surface effect. So.
Exactly. What else? So a third mitigation strategy that you can consider, which has also been, which people already use, is to use more than one detector. The reason is that you expect dark matter to come and interact in only one detector. But tracks that pass through your materials, through your detector, usually emit more than one photon as they pass through. So you can absorb photons in the two detectors at the same time, and then if you have coincident events, you can veto that. In that way, you can get rid of track backgrounds. Another mitigation strategy is highly non-trivial, and to the best of our knowledge, this was never pointed out before too. So one of the big backgrounds at SENSEI and any CCD-like experiment that you build for light dark matter is that you have this doped layer of material in the backside of the CCD, which needs to be there. But there's a process that's called thinning that people use for astrophysical applications, in which they remove lots of the layers in the backside of the CCD while keeping a minimal amount of materials in that backside. And if you do that, then you can reduce the amount of doped, phosphorus-doped surfaces, layers in the backside of the CCD, and this way you can reduce radiative recombination rates. So this is something that actually now the SENSEI collaboration is evaluating if it's worth doing. But it's not trivial that it will help, because you will definitely reduce radiative recombination backgrounds. But at the same time, this small layer of phosphorus allows you to reduce Cherenkov backgrounds, because Cherenkov photons get stuck in the doped layer of the semiconductor, because there the band gap is smaller. So dopants tend to make band gap smaller, so then photons get more easily absorbed there. So it acts accidentally as an absorber. And in fact, if you remove that layer and only count how many Cherenkovs do you have, how many Cherenkov backgrounds, the rate increases by a factor of 100 events per gram day. So it's not trivial that removing this layer will help. It will help you with radiative recombination, but it will hinder you with the Cherenkov. But maybe a win-win situation is that you remove this layer and then you put some other absorbent somewhere else to get rid of the Cherenkovs. Okay, so that will be a win-win situation, but it's a highly non-trivial thing, so that needs to be calculated. So another thing that you can do is that one of the reasons why these low energy photons are so bad is that you produce them and then your detector is within some metallic housing, so they just bounce around until they are absorbed somewhere, and they are usually absorbed in your detector. So one way that you can avoid this is that you coat the copper or any metallic thing that you have in your detector with some paint, say, so that the photons do not bounce around and instead they get absorbed in the paint. Of course, then you need to worry if the paint itself is creating more backgrounds than what it's suppressing, but naively, if you put a thin layer of paint, it's likely that these photons will get absorbed there and you will reduce backgrounds, maybe in a cheap way, I don't know. Yet another mitigation strategy that you can do is, of course, to perform background subtraction. But that's also highly non-trivial. And the reason is that if you want to perform background subtraction, you need to do a simulation about these backgrounds and you need to know your detector extremely well. And you usually don't. For instance, at SENSEI, you have a pitch adapter and a CCD, and in between there's glue, which is this epoxy. The absorption properties of this epoxy, we don't know very well. And they introduce a systematic in our calculations. So if you want to perform background subtraction, you better measure absolutely everything, all the properties of the materials, of the at least big chunks of material in your detector very well, dielectric properties, absorption, impurities, etc. And that's not easy to do. So it's not trivial that it's not completely warranted that you will be able to do background subtraction. At SuperCDMS, on the other hand, for instance, the two PCBs that they have are just some plastic composite, and we really don't know what's a plastic composite. We took some reasonable estimates on what's a plastic or on what's these plastic composites, but we don't have information about it.
So Dennis, sorry for interrupting. So this is not really a mitigation strategy. It's just to understand the backgrounds, right?
Yeah.
You still get like the hit on the sensitivity, right?
Absolutely.
You understand it. Okay, I see. Thanks.
Absolutely. Yeah.
I mean, also, just in terms of understanding this, it looks like the results that you had in a higher radiation environment should sort of do this for you, right? I mean, if you know that you get a certain number of events when your radiation is higher and it's proportional to that, then that sort of tells you where these events are coming from. Or it tells you at least the number that you expect.
Yeah, I mean, you're saying that you can extrapolate the scaling with the number of tracks or something like that.
Yeah,
So yeah, you could try to do that. Just like, yeah, feed the overall number to some particular measurement and then scale back using your calculations. That you can do, but that scaling may also depend on the properties of the materials. I'm not entirely sure.
It shouldn't, right? If you just get a certain number of things for each thing that passes through.
Yeah, that's a good point. That's a good point. But if you're going to do that, then you better make sure that whatever you're measuring, it's from the tracks, which you can do, I guess, to some degree. Yeah. And finally, here we just concentrated on radiative backgrounds for completeness. But let me just point out that there have been very brave proposals towards the future have experiments that detect a very small number of phonons instead of photons. Okay, and let me just say that these backgrounds that I just showed you will also be a source of concern for these experiments. The reason is that in these experiments, they will have a detector where they will detect, or they will hypothetically have a detector where they will detect some few phonon excitations. But any track that passes, for instance, by the holders of the detector, they will lead to, for instance, electron-hole pairs, which then can recombine non-radiatively emitting phonons. And those phonons, if these things are in contact, can make it into your detector and presumably mimic your dark matter signal. Also, if you have tracks passing through the holders of your detector, they can lead to low energy Cherenkov photons, like for the order of 10 to 100 milli electron volts, which then can make it into your detector, be absorbed there, convert into one of the lattice modes of the detector, and in this way mimic a dark matter signal. So this is also a source of concern for low energy phonon proposals. Okay. So just to conclude, we discussed two important backgrounds that affect a variety of dark matter experiments: Cherenkov radiation and radiative recombination. We showed that they are the most likely explanation for the excess events at SENSEI and SuperCDMS, even though we cannot be absolutely sure because there are systematics in the simulation. But as you saw, the numbers point towards the right direction. And we showed also that there are concrete mitigation strategies that you can take towards the future that are likely going to significantly improve the reach to detect dark matter if you're able to reduce these patterns. Thanks a lot.
Okay, yeah, thanks very much, Daniel. That was very interesting to hear about. Does anybody have any more questions? Actually, I'll pause the recording here, I guess. Stop recording.